May 24, 1874, St. Louis, Missouri. The engineering report from visiting European bridge specialists would never fully capture what they witnessed that morning. American steel, supporting the impossible span across the Mississippi River using methods that defied everything European metallurgy said was necessary for structural integrity. Through the steam and hammering of the Missouri construction site, 14 locomotives totaling 550 tons rolled across Carnegie's Bessemer steel bridge with precision that seemed impossible to European observers. No wrought iron, no cast iron supports, no traditional truss design European engineers trusted for major spans, yet they carried loads that European bridge materials could not match. In European foundries, master metallurgists required weeks to produce inferior steel using proven methods. Each batch was inconsistent, different carbon content, different impurities, different strength outcomes. Most carried structural limitations only short spans could accommodate. The Americans were operating with manufacturing philosophy the Europeans had never imagined possible. Vertical integration, quality control at every stage, chemical precision that eliminated guesswork. Production methods that created stronger steel at lower cost than anything Europe produced. 151 years later, the most decisive metallurgical revolution in bridge building history was revealing itself, not in superior raw materials, not in traditional techniques, but in the systematic control that connected every step of steel production, in ways European craft traditions never imagined possible. The Mississippi River stretched half a mile wide in front of James Buchanan Eads, its muddy waters concealing 100 feet of depth down to bedrock. Standing on the St. Louis waterfront in the spring of 1867, the self-taught engineer watched steamboats navigate the treacherous current, while railroad cars sat motionless on the eastern shore, their cargo waiting for ferry transport that could take hours or days, depending on weather and river conditions. The bottleneck was strangling St. Louis commerce, and everyone knew it. Chicago's railroad boom was reshaping American commerce with ruthless efficiency. Direct rail connections between New York and the Western Territories bypassed St. Louis entirely, transforming the once mighty river port into an expensive detour. Merchants who had built fortunes on Mississippi River trade watched their businesses hemorrhage customers to northern routes that moved freight faster and cheaper. The city's survival depended on one solution that seemed impossible: bridging the Mississippi River at St. Louis with a structure strong enough to carry fully loaded freight trains. European engineering firms had studied the problem for years and reached unanimous conclusions. The river was simply too wide and too deep for 19th century materials to span safely. Bridge piers would need to rise 140 feet from bedrock to high water mark, then support spans of 500 feet each, twice the length of any arch successfully built anywhere in the world. Traditional wrought iron, the strongest material proven in bridge construction, would buckle under such massive loads. Cast iron, cheaper but more brittle, would shatter catastrophically under the dynamic forces of moving trains. The European consensus was absolute. No material existed that could safely bridge the Mississippi at St. Louis. Even if such a bridge could theoretically be built, the cost would bankrupt any city or railroad company foolish enough to attempt it. St. Louis civic leaders had consulted the finest engineering minds from London, Paris, and Berlin, receiving identical assessments that the project was decades ahead of available technology. Eads had spent 25 years diving into Mississippi River wrecks, salvaging steamboats from depths that killed most men who attempted such work. His lungs had been compressed by river pressure that European engineers calculated only in theory. His hands had touched bedrock that bridge designers had never seen. While European consultants studied the river from comfortable offices, Eads had walked its bottom, understanding the precise geology and current patterns that would determine any bridge's survival. His radical solution defied conventional bridge design entirely. Instead of the familiar truss structures that European engineers preferred, Eads proposed Roman-style arches made from a material barely 20 years old, steel produced by Henry Bessemer's revolutionary air-blowing process. Steel arches could theoretically carry loads that would destroy wrought iron, but no major structure had ever tested Bessemer steel under real conditions. The material remained experimental, unpredictable, and largely untrusted by conservative engineers. The project would require 2,400 tons of perfect steel, manufactured to specifications that had never been attempted. Every tube would need uniform chemical composition, precise carbon content, and strength characteristics that could withstand twice the expected working loads. Traditional steel suppliers, accustomed to producing material that merely met minimum requirements, balked at Eads's demands for systematic quality control and comprehensive testing. Enter Andrew Carnegie, the ambitious 32-year-old owner of Keystone Bridge Company, who had been following Bessemer's work with intense interest. Carnegie understood that America's industrial future depended on mastering steel production, and the Eads Bridge represented the ultimate test of American manufacturing capability. If Carnegie could deliver steel that met Eads's impossible specifications, he would prove American industry could exceed European standards through systematic innovation rather than traditional craft methods. Carnegie committed to building America's first large-scale Bessemer steel plant, the J. Edgar Thompson Steel Works in Pennsylvania, capable of producing 70 tons of steel per week using the latest air-blowing technology. The investment represented a massive gamble on unproven methods, but Carnegie sensed that conventional approaches would never satisfy Eads's requirements for structural perfection. The harsh realities became apparent immediately. Bessemer's steel production required precise control of furnace temperatures, airflow rates, and chemical composition that no American foundry had ever achieved consistently. Early batches contained phosphorus impurities that made steel brittle in cold weather, sulfur contamination that created internal weaknesses, and carbon variations that produced unpredictable strength characteristics. When the first major contractor, Butcher Steel Works of Philadelphia, attempted to meet Eads's specifications using conventional production methods, they failed repeatedly and eventually abandoned the project, leaving Carnegie facing potential bankruptcy. The bridge project had exposed the fundamental weakness of 19th-century American manufacturing, dependence on suppliers whose quality control and production methods remained beyond the manufacturer's direct influence. Carnegie realized that delivering Eads's specifications would require revolutionary changes in how American industry approached complex projects, conventional steelmaking, buying raw materials from various sources, using standard processes developed by others, accepting whatever quality resulted, could never produce the consistent excellence that modern engineering demanded. Standing in his half-completed steel works, watching another batch of imperfect steel cool in the Pennsylvania autumn of 1868, Carnegie understood that only radical American innovation could bridge the Mississippi River. The solution would require abandoning European craft traditions entirely and developing systematic manufacturing methods that controlled every variable from raw materials to finished product. Carnegie's solution emerged from a radical insight that would reshape American manufacturing forever: control everything or control nothing. Rather than depend on suppliers whose quality varied with market conditions and cost pressures, Carnegie decided to own every step of steel production from iron ore extraction to finished bridge components. This vertical integration represented a fundamental departure from European industrial organization, where specialized firms handled individual stages of production while relying on market mechanisms to coordinate the entire process. The acquisition campaign began in 1868 with Carnegie's purchase of extensive mineral rights in Minnesota's Mesabi Iron Range, the richest iron ore deposits discovered in North America. These mines contained ore with iron content exceeding 60%, dramatically superior to the lower-grade materials available to European competitors. Carnegie's geologists had identified specific ore bodies with minimal phosphorus contamination, the chemical impurity that made Bessemer steel brittle and unreliable. By controlling ore selection at the source, Carnegie eliminated the quality variations that plagued conventional steel producers who purchased materials on spot markets. Carnegie simultaneously acquired coal mines throughout Pennsylvania's Connellsville region, where geological conditions produced coal ideal for coke production. Coke manufacturing required precise control of carbon content and heating rates that commercial suppliers rarely achieved consistently. Carnegie's mining engineers developed systematic extraction methods that delivered uniform coal composition, while his coke ovens used controlled heating cycles that eliminated impurities other producers accepted as inevitable. The integrated approach meant Carnegie's steel furnaces received fuel with predictable characteristics, enabling consistent furnace temperatures and chemical reactions. Transportation represented the next critical link in Carnegie's vertical integration strategy. Rather than rely on independent shipping companies and railroads whose schedules and handling methods could damage materials or create costly delays, Carnegie purchased his own fleet of Great Lakes ore ships and railroad lines connecting mines to mills. His ships featured specialized holds designed to prevent ore contamination during transport, while his railroads used dedicated cars that eliminated mixing of different ore grades or coal types. This transportation control eliminated the quality degradation and scheduling uncertainties that handicapped competitors using common carriers. The breakthrough impact became apparent immediately in Carnegie's expanded Thompson Steel Works, where systematic quality control replaced the guesswork that characterized traditional steel production. Carnegie's mining foremen inspected every ton of ore before loading, rejecting materials that failed chemical composition tests. His transportation managers tracked each shipment from mine to furnace, maintaining detailed records that enabled correlation between raw material sources and finished steel properties. His furnace operators received materials with known characteristics, enabling precise control of smelting processes that produced consistent results. Captain William Jones, Carnegie's brilliant superintendent despite lacking formal engineering education, transformed this material control into manufacturing excellence through obsessive attention to operational details. Jones instituted systematic testing at every production stage, from incoming raw materials through intermediate processes to finished steel tubes. His workers measured furnace temperatures every 15 minutes, recorded the exact timing of each air blast during the Bessemer process, and documented the chemical composition of every batch before pouring. This data collection enabled Jones to identify the precise conditions that produce superior steel, then replicate those conditions consistently. The economic impact proved as revolutionary as the quality improvements. In 1870, American steel cost $166 per ton, making large construction projects prohibitively expensive for most applications. Carnegie's integrated system eliminated the profit margins and inefficiencies of multiple suppliers while enabling economies of scale impossible under conventional organization. By 1871, Carnegie's steel cost $90 per ton, while exceeding the quality specifications that other producers could not meet at any price. The cost advantage funded continuous improvements in equipment and processes that widened Carnegie's competitive lead. Carnegie's vertical integration also eliminated the coordination problems that plagued complex projects like the Eads Bridge. Traditional manufacturers faced constant delays when suppliers failed to deliver materials on schedule or delivered substandard materials that required replacement. Carnegie's integrated system enabled precise scheduling because he controlled every input. His mines delivered ore on predetermined schedules. His railroads transported materials without delays caused by competing freight, and his furnaces operated continuously without interruptions caused by supply shortages. The systematic approach enabled Carnegie to guarantee delivery schedules and quality specifications that no competitor could match. While European bridge builders faced months-long delays waiting for acceptable materials, Carnegie's integrated production delivered bridge components exactly when construction schedules required them. This reliability allowed Eads to plan bridge construction with confidence, knowing that steel deliveries would not create costly delays that could destroy project financing. Carnegie's method also enabled rapid innovation cycles impossible under conventional industrial organization. When early steel batches revealed specific quality problems, Carnegie's metallurgists could trace the issues back to particular ore deposits, coal seams, or furnace operating conditions, then implement corrections throughout the integrated system within weeks. Competitors relying on independent suppliers faced months-long delays in implementing improvements because coordination required negotiations with multiple firms whose interests often conflicted. By 1871, Carnegie's integrated system was producing steel that consistently met Eads's demanding specifications while generating profits that funded further expansion and improvement. The vertical integration strategy had transformed experimental Bessemer technology into reliable industrial production, proving that American systematic organization could achieve what European craft traditions had declared impossible. Carnegie had created not just a steel company, but a new model of industrial organization that would define American manufacturing supremacy for generations. Construction of the bridge superstructure began in earnest during the spring of 1872, with Carnegie's steel arriving at the St. Louis construction site in precisely machined 18-inch diameter tubes that would form the structural ribs of Eads's revolutionary arch design. Each tube had to meet testing standards that no structural steel had ever faced in American construction. Eads demanded that every component withstand load testing to 8,000 pounds per square inch, double the maximum stress the bridge would ever experience under normal operating conditions, including fully loaded freight trains crossing simultaneously. The testing regime went far beyond conventional construction practices that relied primarily on visual inspection and basic strength calculations. Carnegie's metallurgists subjected each steel tube to comprehensive chemical analysis, verifying carbon content within narrow tolerances that eliminated the strength variations plaguing traditional iron construction. Phosphorus content could not exceed 0.04%, while sulfur contamination had to remain below 0.05%. These specifications required analytical precision that most American foundries had never attempted, much less achieved consistently. Physical testing protocols established by Eads pushed structural materials beyond any previous standards in bridge construction. Every tube underwent systematic hammering tests designed to reveal internal flaws that might cause catastrophic failure under dynamic loads created by moving trains. Workers struck each tube with standardized hammers, while experienced inspectors listened for the distinctive sound patterns that indicated internal weaknesses or inconsistent material density. Tubes that failed these acoustic tests were rejected regardless of their visual appearance or basic strength measurements. The most demanding requirement involved proof-loading every major structural component before installation. Carnegie's workers suspended test weights from steel tubes until they carried exactly twice the maximum load Eads calculated for bridge service conditions. The tubes had to support these extreme loads for extended periods without showing permanent deformation or developing stress cracks visible to trained inspectors. This testing destroyed dozens of tubes that met conventional standards, but failed Eads's extraordinary requirements for structural reliability. Carnegie's response to these unprecedented demands revealed the revolutionary potential of systematic American manufacturing. Rather than protest Eads's specifications as impossible or commercially unrealistic, Carnegie embraced them as opportunities to develop manufacturing capabilities that would establish permanent competitive advantages over European producers. His Thompson Steel Works became America's first industrial facility, organized around systematic quality control rather than simple production volume. Captain Jones implemented testing protocols that tracked every steel tube from raw materials through finished product, creating detailed records that enabled continuous improvement of manufacturing processes. His workers recorded furnace temperatures during each stage of the Bessemer process, documented the exact duration of air blasting required to achieve optimal chemical composition, and measured cooling rates that affected final material properties. This systematic data collection enabled Jones to identify the precise conditions that produce steel exceeding Eads's requirements, then replicate those conditions consistently. The human element proved as crucial as technological innovation in meeting Eads standards. Jones worked 16-hour days personally supervising critical operations, arriving at the steel works before dawn to inspect furnaces, and remaining until late evening to oversee the final stages of steel production. His direct involvement in every aspect of manufacturing enabled rapid identification and correction of problems that would have caused delays or quality failures under conventional management approaches. Jones developed an intuitive understanding of steel production that complemented systematic testing protocols with practical experience gained through years of hands-on work. He could diagnose furnace problems by listening to the sounds of combustion, predict the quality of finished steel by observing the color and behavior of molten metal during pouring, and detect potential equipment failures through subtle changes in operational patterns that formal measurements might not reveal immediately. The systematic approach produced remarkable results that validated Carnegie's strategy of exceeding rather than merely meeting customer specifications. By the end of 1872, Carnegie's Thompson Works had delivered 150 perfect steel tubes that met or exceeded every one of Eads's demanding requirements. Each tube carried detailed documentation of its chemical composition, strength characteristics, and testing history that provided complete traceability from raw materials through finished product. Bridge construction accelerated dramatically once reliable steel deliveries enabled Eads to implement his innovative cantilever construction method. Traditional bridge building required extensive temporary supports that interfered with river navigation and created dangerous working conditions during Mississippi River floods. Eads's cantilever approach built the bridge outward from each pier without requiring support below, enabling continuous construction regardless of river conditions while maintaining safe navigation channels for steamboat traffic. The cantilever method also demonstrated the superior properties of Carnegie's steel compared to traditional iron construction materials. Each arch section had to support not only its own weight, but also the weight of subsequent sections during construction, creating temporary stress conditions that exceeded the bridge's final operating loads. Carnegie's steel handled these extreme construction stresses without permanent deformation or structural damage that would have been inevitable with conventional iron materials. Construction progress became a public spectacle as St. Louis residents watched the impossible bridge take shape over their river. The massive stone piers rose steadily from bedrock to high water mark, their foundations deeper than any construction project previously attempted in America. The steel superstructure grew outward from each pier with mathematical precision, each section fitting perfectly with adjacent components, despite the enormous spans involved. By early 1873, the bridge structure was 75% complete, with Carnegie's steel proving its superiority through every stage of construction. The systematic manufacturing methods that had seemed unnecessary to conventional producers now appeared prophetic as competitors struggled to deliver materials meeting even basic construction requirements. Carnegie had established American steel production as superior to European alternatives through the systematic excellence that characterized all his operations. The financial panic of 1873 struck with devastating suddenness, beginning with the collapse of J. Cook and Company in September and spreading through American financial markets like wildfire through dry timber. Railroad construction projects across the nation halted as investors withdrew capital and banks refused to extend credit for speculative ventures. The St. Louis Bridge Company, dependent on Eastern financing to complete construction, found itself unable to meet payroll obligations or purchase materials as credit markets froze completely. Construction of the Eads Bridge ground to an abrupt halt, with the structure tantalizingly close to completion. 3/4 finished, the massive stone piers stood like monuments to interrupted ambition, while the partially completed steel arches stretched across the Mississippi River, like skeletal fingers reaching toward goals they would never achieve. Workers abandoned the construction site as the bridge company declared bankruptcy, leaving tools and equipment to rust in the autumn weather of 1873. The financial crisis delivered a more devastating blow to Carnegie's reputation than any engineering failure could have inflicted. Investors who had supported his innovative steel production methods now questioned whether Bessemer technology was commercially viable under normal market conditions. The bridge project had consumed enormous resources developing manufacturing capabilities that seemed useful only for meeting Eads's extraordinary specifications. Critics argued that Carnegie had over-engineered solutions to problems that conventional methods could have solved more economically. Carnegie himself lost faith in the project that had defined his transition from bridge contractor to steel manufacturer. Facing mounting losses from the suspended construction and declining orders from other customers affected by the financial panic, Carnegie sold his bridge company stock at panic prices to raise cash for his steel operations. His private correspondence from this period reveals deep frustration with what he termed the affair, and genuine uncertainty about whether American steel could compete commercially with traditional iron materials. The technical challenges that had seemed manageable during periods of steady progress now appeared insurmountable obstacles to commercial success. Early Bessemer steel production continued to suffer from phosphorus contamination problems that made the material brittle in cold weather, exactly when bridge structures face their greatest stress from ice loads and thermal contraction. Carnegie's metallurgists had conducted thousands of experiments attempting to eliminate phosphorus impurities, but consistent results remained elusive despite enormous expenditures on research and development. Nitrogen contamination presented an equally serious problem that conventional steelmaking approaches could not solve reliably. The Bessemer process relied on blowing air through molten iron to burn away impurities, but the nitrogen in atmospheric air created chemical reactions that weakened the finished steel in ways that were difficult to predict or control. Some batches of Carnegie steel exhibited excellent properties during initial testing, but developed internal flaws over time as nitrogen contamination caused gradual deterioration of structural integrity. Competitors exploited these technical problems to undermine confidence in Bessemer steel throughout the American construction industry. Bridge collapses elsewhere in the country, while unrelated to steel quality, were attributed to the experimental nature of Bessemer technology by iron manufacturers who had invested heavily in traditional production methods. Trade publications carried articles warning engineers against using untested materials in critical applications, citing the financial failure of the Eads Bridge project as evidence that systematic quality control could not overcome fundamental deficiencies in the steelmaking process. The rumors spread that Bessemer steel was rotten hot and rotten cold gained credibility even among engineers who had initially supported Carnegie's innovative approaches. The phrase captured widespread fears that steel became dangerously weak at both high and low temperatures, making it unsuitable for bridges that had to withstand summer heat and winter cold throughout their service lives. These technical concerns combined with financial uncertainty to create a crisis of confidence that threatened to destroy the American steel industry before it could fully develop. Carnegie's integrated manufacturing system, which had seemed like a competitive advantage during successful operations, now appeared to be a costly mistake that tied up excessive capital in specialized facilities. Critics argued that vertical integration made Carnegie's operations inflexible and vulnerable to market downturns that affected multiple stages of production simultaneously. Traditional iron manufacturers who relied on independent suppliers could reduce costs quickly during economic contractions, while Carnegie's fixed investments in mines, transportation, and manufacturing required continuous operation to remain economically viable. The half-completed bridge became a powerful symbol of American industrial overreach and the dangers of abandoning proven European methods for experimental technologies. St. Louis newspapers published editorials questioning whether the city had been wise to reject traditional bridge designs in favor of Eads's revolutionary arch concept. Business leaders who had supported the project now distanced themselves from what appeared to be a spectacular failure that would leave the city with massive debts and no functioning bridge. Carnegie's steel tubes, which had been celebrated as examples of American manufacturing excellence, now darkened with rust as they sat exposed to Mississippi River weather without protective maintenance. The visual deterioration of the unfinished bridge structure provided compelling evidence for critics who argued that steel was inherently less durable than traditional iron construction materials. Each winter storm and spring flood seemed to confirm that the experimental bridge would never justify the enormous investments in new technology and manufacturing methods. The crisis reached its nadir during the winter of 1873 to 1874, when Carnegie privately acknowledged that the Eads Bridge project might represent a permanent failure of American steel technology. His letters from this period reveal a man struggling with the possibility that systematic manufacturing methods and vertical integration could not overcome the fundamental technical challenges of producing reliable steel for major construction projects. The dream of American industrial supremacy based on systematic innovation rather than traditional craft methods seemed to be dying along with the abandoned bridge construction. The breakthrough that would save both Carnegie's reputation and American steel technology came from an unexpected source in the form of Robert Forrester Mushet, an English metallurgist whose systematic experiments in his modest laboratory had unlocked the secret that had eluded larger industrial operations. Mushet's discovery was elegantly simple yet revolutionary. Instead of trying to prevent contamination during the Bessemer process, burn away all impurities completely, then add back precise amounts of carbon and manganese using Spiegeleisen, a ferromanganese alloy that restored strength while eliminating brittleness. Mouchet's breakthrough solved the fundamental problem that had plagued early Bessemer steel production by transforming contamination control from guesswork into precise chemical engineering. His process involved two distinct stages that enabled systematic quality control impossible with conventional methods. First, the Bessemer air blast continued until all carbon, nitrogen, and other impurities were completely eliminated, creating pure iron that was too soft for structural applications but free from the contaminants that caused unpredictable weakness. Second, carefully measured amounts of Spiegeleisen were added to restore carbon content to exact specifications while introducing manganese that neutralized residual sulfur and phosphorus. Carnegie immediately recognized that Mouchet's two-stage process was perfectly suited to his integrated manufacturing approach, which controlled raw material quality from ore extraction through finished products. While competitors using conventional suppliers struggled to implement Mouchet's method because they could not guarantee the purity of incoming materials, Carnegie's vertical integration enabled precise control of every variable affecting steel chemistry. His Minnesota ore contained minimal phosphorus contamination. His Pennsylvania coke provided consistent carbon content, and his transportation system prevented mixing of different material grades. The systematic application of Mouchet's discovery at Carnegie's Thompson Steel Works produced results that exceeded even Eads' demanding specifications for bridge construction. Carnegie's metallurgists could now predict steel properties with mathematical precision by controlling the exact amounts of Spiegeleisen added during the final stage of production. Chemical analysis of each batch verified carbon content within 0.01% tolerance, while manganese levels remained equally consistent throughout large production runs. By early 1874, Carnegie had perfected the Mouchet process to achieve steel quality that surpassed anything available from European producers. His integrated system eliminated the quality variations that plagued conventional steelmaking by controlling every factor that affected final product characteristics. Ore composition, coke purity, furnace temperatures, air blast duration, and Spiegeleisen additions were all monitored and adjusted systematically to produce steel with predetermined properties that could be replicated consistently. The financial recovery of the bridge project followed the technical breakthrough as new investors recognized that Carnegie's systematic approach had solved the reliability problems that had caused the original financing collapse. The combination of proven steel quality and Eads' innovative cantilever construction method now appeared commercially viable rather than dangerously experimental. Construction resumed in the spring of 1874 with confidence that both materials and methods would deliver the promised results. The ultimate vindication came with the bridge testing program that began on May 24, 1874, designed to prove definitively that Carnegie's steel could handle loads far exceeding normal service conditions. The first test involved an elephant walking across the completed structure, based on the popular belief that elephants possessed instinctive ability to detect unsafe conditions and would refuse to cross unstable bridges. The elephant crossed without hesitation, providing dramatic evidence of structural integrity that captured public imagination while serving as genuine proof of the bridge's stability. The definitive engineering test involved 14 locomotives totaling 550 tons positioned across the bridge simultaneously, creating loads that exceeded the maximum stress calculations by substantial safety margins. The locomotives remained stationary on the bridge for extended periods, while engineers measured deflection using precise instruments, then moved slowly across the structure while observers monitored any signs of excessive flexing or vibration. The bridge performed flawlessly, showing no measurable deflection under loads that would have destroyed conventional iron structures. The July 4th, 1874 grand opening celebration provided triumphant vindication of both Eads' engineering vision and Carnegie's manufacturing methods. General William Tecumseh Sherman drove the ceremonial last railroad spike, while 100 cannons fired in celebration of American engineering achievement. The first official train crossing marked the successful completion of the longest arch bridge ever built and the first major structure constructed entirely from Bessemer steel. Eads' prediction that the bridge would stand as long as it is useful proved remarkably accurate as the structure continued handling heavy traffic loads year after year without the maintenance problems that plagued iron bridges of similar vintage. The 2,400 tons of Carnegie steel showed no signs of deterioration or fatigue despite carrying millions of crossings by increasingly heavy locomotives. Bridge inspections revealed that the systematic quality control implemented during construction had produced structural materials superior to anything previously available. The long-term vindication became even more dramatic as decades passed and the bridge continued operating without major structural problems. Rehabilitation work conducted in 2016 found that Carnegie's original 1874 steel remained structurally sound after 142 years of continuous service. Modern analysis revealed that the chemical composition of Carnegie's steel exceeded current industry standards for structural applications, demonstrating that his systematic approach had achieved quality levels that contemporary manufacturing struggled to match. The contrast with modern construction became increasingly apparent as interstate highway bridges built during the 1960s required replacement after only decades of service, while bridges constructed during the 1980s showed dangerous corrosion that threatened public safety. The fundamental difference lay in manufacturing philosophy. Modern steel production focused on meeting minimum code requirements as economically as possible, while Carnegie's integrated approach had emphasized exceeding every specification through systematic control of all production variables. Today, 8,100 vehicles cross the Eads Bridge daily, alongside 300 Metrolink trains, testament to the durability achieved through Carnegie's systematic manufacturing methods. 151 years of faithful service proved that American industrial innovation based on vertical integration and systematic quality control could create products superior to anything achievable through conventional approaches that accepted minimum acceptable standards rather than pursuing maximum possible excellence.